And we're back. Welcome back and happy Thursday. Today, we will discuss properties of the hypothesis set by introducing a framework for how we characterize the performance of your hypothesis set on a data set. Okay, so before we begin, a few administrative bits. The reading. Chapter 2, sections 2.1 through 2.2. And when I say through 2.2, I mean including section 2.2. Project number 1 is due this Tuesday, the 10th of February, 2021, at the usual 11:59 and 59 seconds. That's 11:59 and 59 seconds. So we talked last time about adding an error measure, and this error measure described the coincidence between the working hypothesis and the unknown target function's labeling action on the training examples. So let's take a look at training and testing. We talked about Hoeffding's inequality, and Hoeffding's inequality is a theoretical framework that said if you strike the right balance between your error tolerance, epsilon, and the size of your training set, n, your in-sample points, that you can guarantee that the likelihood that E out will diverge from En is very or relatively rare. So that means En and E out will track with one another. You have control over En, but you don't know really what E out is. We took that example and we generalized it by introduction of a probability distribution over the input space, and we said that probability is responsible for giving us the feature vector instantiations that we see. And in doing so, we included the learning algorithm with what we know about Hoeffding's inequality, treating this condition that En and E out diverged by more than error tolerance epsilon as a notional bad event. And then that allowed us to put an upper bound on the probability that as we search and visit one working hypothesis to the next, searching for that final best hypothesis G, that we model this set of bad events, the union of them in the Venn diagram, and the upper bound that allowed us to bound all of these instances of Hoeffding's inequality using the union bound, and it gives us this complexity measure M, which describes the size notionally, or the complexity more correctly, of the hypothesis set. And with the union bound, we had something that looked more like learning, this search through the space of hypotheses for that final best hypothesis G, and we found that we now have to make a trade-off, strike a balance between the complexity of the hypothesis set M, the size of the in-sample points, big N, and the error tolerance, epsilon. And if we can strike this appropriate balance between the three, we can assure that En will diverge from E out. They track together, but that divergence will be very rare. But if not, if our M, our hypothesis set, is too complex, well, then all bets are off. It's going to diverge very often because the right-hand side of this union bound for Hoeffding's inequality is going to be close to 1. Okay, so let's examine more correctly this notion of a bad event. And let's now describe this condition over which we define our probability for Hoeffding's inequality, that En tracks E out for a given hypothesis. Let's call that our bad event, and we'll just note that as Bm. Now, of course, when we apply the union bound, we're looking at the probability that we get the first bad event for H1, the second bad event for H2, so forth, up to and including the mth bad event, Bm. And we said that in the worst case, the upper bound of Hoeffding's inequality, the union bound version, made the simplifying assumption that these bad events do not overlap. But if you think about what a hypothesis is, if you have two hypotheses, they could be very close to one another. If we look at a weight vector, let's say we have weight vector W1, and that's some value. Maybe W0 is 10, W1 is 11.5, maybe W2 is 12.6. If we had another hypothesis defined by W2, maybe that value is 10.01, 11.51, and 12.607. Now, of course, W1 and W2 are very close to one another. And because they're very close to one another, if we look at their performance in the input space, they're not going to be terribly different from one another. So what does that mean in terms of the union bound on Hoeffding's inequality? It means that this assumption given by the union bound is a simplifying assumption. It's the absolute worst case. But what we find in practice is that these bad events, E in diverges from E out for a given hypothesis, these bad events from one hypothesis to the next, and we see that with W1 and W2 in this example, they're not going to be completely divergent. They're going to overlap to a large degree. And this is what happens in practice. So when we count the size of the hypothesis set, we can do better, because at the end of the day, even for a two-dimensional hypothesis, W1, W2, augmented by W0, there are an infinite number of instantiations you can have for your weight vectors because they're real numbers, they're scalars. So we can do better than this infinite M. So these bad events can overlap. Let's take a more geometric example. And we're going to look at our two-dimensional feature space. And we're going to have two hypotheses. Let's call this first one, the blue line on the plane, H1. They're linear hypotheses. And let's call this green line on the plane, call that H2. So we have two hypotheses, and they're very similar to one another. They're not far off. And that's exactly the case like we saw before. If you have two weight vectors, linear hypotheses, whose numerical positions, their weights, are not different from one another. And so if we take H1, H1 is going to classify everything on the upper right as being +1. So H1 is going to say everything here is +1. And H1 is consequently going to say everything here is going to be -1. Now, of course, in our feature space, we have colored the regions of the feature space representing the ground truth labels out of sample. And the gray area is the ground truth out of sample +1 points, the positive instances. And the light gray, or off-white, if you want to call it that, regions of our feature space are the -1 values, instantiations. And those are our negative examples. So we have all the ground truth plus labels out of sample and all the ground truth -1 labels out of sample. And so anything in this triangular region is going to be out of sample error as it pertains to H1. Because H1 says it should be +1 and ground truth, it's -1. It's light gray. Likewise, all of the gray shaded area here between the blue line and that boundary, those are also going to be out of sample errors, because H1 says that everything over here should be -1, but ground truth is +1. So these are the out of sample errors for H1. Now, if we look at the out of sample error for H2, well, H2, likewise, if we take all of the area on this side of H2, H2 says that should be +1, and H2 says everything on the other side of the green line should be -1. So we have all the errors, out of sample error for H2 is the shaded region from this green line, including this triangular section. Likewise, Likewise, we have all of the shaded region from the green line going down and to the left. That's also out of sample error with respect to H2 for the dark gray region, plus the sliver. Now, of course, if you have a change in hypothesis, a slight change, you can see they're out of sample error. They're not very different from one another. They're very close by. And in fact, the difference in out of sample error for between H1 and H2 is this yellow sliver here between the two hypotheses. And so if we wanted to look conversely at the in-sample error would be at the examples. And so if we look at each of these data points, those are our in-sample points, and this is what we actually see in practice. So if we look at these points, well, in sample, their ground truth label is +1. These points in the light shaded region, their ground truth class label is -1. These points, their ground truth label is +1 because they're in the gray shaded region. And these points, these two up here, their ground truth label is -1 because they're in the off-white light gray region. Now, of course, these points are going to be in error. And for these 2 points, hypothesis H1 says that they're +1 when ground truth they're -1. And for these 2 points, hypothesis H1 says they should be -1 when ground truth they're +1. And so for H1 and also H2, H2 agrees for these points. H2 says, okay, these should be +1 and ground truth are -1. H2 also says these two should be -1, but they're actually ground truth +1. And so when we look at the in-sample error, we see that there's actually no difference between H1 and H2. So let's carry this assumption forward, because there's no difference between H1 and H2, and we know the change in E out is relatively small. This bad event overlaps to a large degree. So one of the things we can do is we can replace out. Instead of counting all of the infinitely many instantiations of the weight vector corresponding to our hypotheses, we can take this infinite set of hypotheses and collapse it down into something that's more manageable. So in a way, what we want to do is count the number of hypotheses that we have for a hypothesis set. Now, of course, instead of using the whole hypothesis space, we only consider hypotheses whose outputs are different on a single point. And so we're going to define the hypotheses not in terms of, in particular, when we're counting them in terms of the weight vector, number of instantiations, we're going to count them in terms of their ability to produce labels, different sets of labels, on the in-sample points. So in considering a finite input set, because our set of in-sample points is finite, we restrict ourselves and we effectively collapse the space of infinitely many hypotheses down into an equivalence class. And that equivalence class is defined by the labeling of that hypothesis on those in-sample points. So if we have this purple hypothesis as H1, and let's say we have another hypothesis, this blue line, I'll just call that H2. Well, for all intents and purposes, H1 and H2 are the same hypothesis because they produce the same labeling on the in-sample points. And so we eliminate this idea of the ground truth labeling out of sample, and we think only in terms of counting the hypotheses based on their equivalence class, how they label the in-sample points. So in the case of H1 and H2, we strip away all of the out-of-sample values. So we go from here, the blue and the pink, to the gray. And then we take our data points based on their position of feature space, and then we apply the two hypotheses. And so H1, we'll call these blue, +1, and those pink, -1, that's H1, and H2 is counted as the same hypothesis or equivalence class because it produces the same labeling. Those three are blue, and these three are pink, the -1. And so in doing so, we wipe out the input space, and we just count the number of so-called dichotomies. And a dichotomy, I'll define in the next slide or two, is just a labeling, an assignment of +1, -1 labels to our in-sample points. And so this count of the number of different labelings a hypothesis can make, a hypothesis set can produce, is going to be a measure of the strength or the descriptiveness of that hypothesis. How many ways can it bend and twist and fold to produce a different labeling for our input or our in-sample points? And so we have our hypothesis, and the hypothesis operates on the set of inputs, a real value d-dimensional space, and it assigns a label either +1 or -1 to each one of the input vectors that are in-sample points. And so we'll define a dichotomy. A dichotomy is some labeling of all of our input points, our in-sample points. And so we have vector x1, vector x2, x3, and so forth, up to and including xm. And each one of them is going to be assigned a label, +1, -1. So here, when we talk about dichotomies, we're going to restrict ourselves to all of the inputs, the set of in-sample points. And so when we look at the number of hypotheses, if we were to think of a hypothesis set in terms of the raw count, the number of hypotheses, weight vector instantiations, this can be infinite. But when we think in terms of dichotomies, we're taking plus, 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 minus, minus, minus. You can have a very large number of hypotheses, H1, H2, a potentially infinite number, H3, etc., of hypotheses, and you're collapsing them all down into one equivalence class as the hypothesis that produces a particular dichotomy. And so the number of dichotomies, if we were to count the number of dichotomies, that's going to be at most 2 to the n, where n is the size of the set of the in-sample points. And so in this gives us a collapsing of this infinite measurement for the size of the hypothesis set, gives us an upper bound on the number of dichotomies, even though our hypothesis set started out as being infinite. And so this is going to be our candidate, this idea of the collapsing down of the counts into something that's bounded, something that's finite. We're going to use this as a way of replacing this m from the union bound for Hoeffding's inequality for the measurement of the complexity of our hypothesis set. And so let's define a new terminology. Let's define the growth function. And the growth function m is associated with the hypothesis set, so we use a subscript m sub h. The growth function for hypothesis set h, given a data set of size n, that's our in-sample points, is going to be the maximum number of dichotomies the hypothesis set can produce, the maximum number of labels. And so this growth function satisfies this upper bound if we look at all the ways we can assign +1, -1 labels to these n many data points. Well, there are 2 choices for the first one, times 2 choices for the second one, times 2 n many times. That's 2 multiplied with itself n many times. That's 2 to the n. And so the biggest that our growth function, the biggest value the growth function can take on is going to be 2 to the n, because that's the maximum number of dichotomies any hypothesis set can produce, because that's the maximum number of labelings of +1, -1 you can have with a data set in sample points of size n. So the growth function satisfies this inequality. Growth function of hypothesis set h, given in-sample data of size n, is at most 2 to the n. Now, this is a dramatic improvement on infinity, and we can use our growth function in place of m whenever we're dealing with these multiple hypotheses, because we're effectively collapsing a large number of them into a single equivalence class based on their ability to produce different set of labelings for the Insample points. So let's go ahead and carry this definition forward, and let's look at growth function for the perceptron. Now, of course, when we say growth function, we want the maximum number of labelings. And so we're not going to give any regard to the probability distribution that gives us our features. We don't care what those features are. And because we don't care what those features are, we don't care about the placement of the points, the geometry of the points in feature space. But we're after the absolute maximum number of labelings, plus one, minus one, dichotomies, that the hypothesis set can produce. So let's take a look at the growth function of the perceptron, line on the plane, our linear hypothesis. Now, of course, if we had a data set of size 3, I'd direct your attention to the center frame. If we had the points lined up in the following fashion, this particular labeling, a linear hypothesis, cannot produce. It can't, because to produce this blue, you need something that bends, and a straight line doesn't bend. Now, of course, that's not advantageous. We said that it doesn't matter where the points are in feature space. So when you do this analysis for the growth function, you can position our points in feature space any way you want, as long as you can maximize the number of dichotomies that the particular hypothesis set can produce. And so I'll direct your attention to the frame on the left-hand side. For that same n equals 3, if they're arranged in the following way, well, growth function we can produce with the perceptron line on the plane, we can produce 8 dichotomies. So what are those 8 dichotomies? Well, if we put the perceptron here, we get all red and no blue. If we put the perceptron here, we get all red, no blue. So that's 2. We can partition off this one, so we can get that red and we can get blue. And we can do it the other way, so that we get blue and red. So that's 1, 2, 3, 4, 5, 6, 7, 8. So that's 8. Now, if we look at the maximum number of dichotomies that we can produce, that's 8 with the perceptron, given a data set of size 3. And guess what? The upper bound is, well, 2 times 2 times 2, 2 to the n, where n is 3, is 8. Okay. So for this case, the perceptron, that linear hypothesis line on the plane, can produce all 2 to the n dichotomies, or labelings. Okay. But when we go to n equals 4, well, we can only produce 14 dichotomies given a data set of size 4. So what is that? All right, well, we have here, that's 1. We have 2, so that's all red or all blue. And we can separate them off one at a time. So that's 2 here, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then we can separate off 2, 11, 12. And then we have 13 and 14. Now, of course, I'm counting twice, because for one of them, this one can say red while the other is blue, and this one can say blue while the other side is red. So we have a total of 14 different dichotomies, labelings, plus 1, minus 1 for each one of these data points in feature space that the perceptron can make when the data set size is 4. Now, of course, if we look at the maximum number of dichotomies for a data set of size 4, well, that's 2 times 2 times 2 times 2, that's 16. So we notice here that the growth function for the perceptron line on the plane, it's short 2 dichotomies. So it cannot fully express all possible dichotomies on a data set of size 4 once we go to 4. And so at some point, when we increase the data set size, we go from data set of size 3 to size 4, something breaks. The perceptron is no longer able to produce all 2 to the n dichotomies. And so that means it's not expressive enough to continue once we have data set size n equals 4. It's not expressive enough to continue producing all possible growth, all possible dichotomies. And so let's take a look at some examples, hypotheses, and we'll demonstrate with this just what we mean by this notion of descriptive power by looking at the growth function and counting dichotomies. And so here's a simple hypothesis called the positive ray. And this positive ray has an anchor point. We call that value A. And along this number line, we have one-dimensional feature space. And each of our in-sample points, big N of them, has just a single value. And so this positive ray operates in the following fashion. It has anchor point A, the parameter that defines it. Wherever you set A, the anchor point for the ray starts there, and it points off to the right infinitely. All of those data points that it covers along the line, along the ray as it extends to the right, those are going to have an output from the working hypothesis, this positive ray of +1. Everything to the left is going to be -1. And so we have our hypothesis, and it takes a real valued feature, and it outputs a label +1, -1. Functionally, if you're going to write out this expression for the hypothesis, and you can code this in 1 or 2 lines of MATLAB, h of x, a working hypothesis, is sine of x minus a, where a is the position of the anchor point. And so if we look at the growth function for the positive ray, well, the growth function says how many different dichotomies can you produce? Well, if we look at all the places we can place the anchor, that'll tell us all the different dichotomies you can produce. And so here we have n data points, and if we were to count the number of segments where we can place our anchor point, that's 1 going to the left of each point, 2, 3, 4, up to and including n, add another one here, and that's n plus 1. And so for each one of those positionings of the anchor point A for our positive ray, we get a different labeling, +1, -1, for our n many in-sample points. And so this is the growth function of the positive ray. Let's continue and make our hypothesis set a little bit more descriptive. We're going to call this the positive interval. Now, this positive interval is more expressive. It has 2 anchor points. We have the anchor point on the left, and we have the anchor point on the right. The semantics of this is such that when we place the 2 anchor points somewhere on the line, and it's a one-dimensional feature space, all of those in-sample points that are between the left and the right anchor points are going to get a label of 1. And then all of those that are outside of that interval between the left and right anchor point, to the left or to the right, they're going to get a label of -1. And so if we want to count the number of dichotomies, this assignment of +1, -1 labels of this hypothesis, the set of positive hypothesis set, the set of positive intervals, if we want to count the number of dichotomies that it can produce, i.e. its growth function, we would count the number of ways we can place these 2 anchor points. And so how can we place these 2 anchor points? We have 2 anchor points, so we're going to make 2 choices about where we're going to place these anchor points. And so how many parts of the line can we place it on? We have 1, 2, 3, 4, 5, up to including n plus 1. So that's going to be n plus 1, choose 2, because we're going to choose one anchor point and choose the other anchor point out of these n plus 1 line segments, either to the left of the extreme point, to the right of the extreme point on the high side, or somewhere in between the others. But we're not done, because another dichotomy we can create is if the 2 anchor points are on the same line segment, well, that means that there are no blue labeled points and everything is labeled red. So we're going to add one more for that case where both anchor points are in the same line segment. So that means we have n plus 1, choose 2. That's for the placement of the 2 anchor points left and right in different line segments, plus 1 where that one case where the anchor points are on the same line segment. And placing them on the same line segment, there's only one labeling that will produce. Because if you place them on this one and this one, it's the same labeling as placing them on this one and this one. Because remember, what we're counting is unique out? Well, n plus 1 choose 2. That's n plus 1 factorial, so it's n plus 1 times n minus 1 factorial over n minus 1 minus n plus 1 minus 2. That's n minus 1 factorial over 2 factorial. Well, of course, the n minus 1 factorial, n minus 1 factorial, those cancel, and we're left with 2 factorial in denominator. That's 2 times 1. So that is 2 over, we carry that multiplication, n squared plus n, and then we have that plus 1 from before, plus 1. And so we expand this, we get 1/2 n squared plus 1/2 n plus 1, and there's the closed form expression for a growth function for the positive intervals. Okay, so let's consider a more expressive hypothesis set. And this hypothesis set is the set of convex sets, and it's defined in two-dimensional feature space. And again, we set no restriction on the probability distribution that gives you the feature vector instantiation. So what we're going to do is we draw a circle in feature space, and then we sample along the circle in feature space, and we make any assignment of +1 or -1 to the points along the circle. And we then go to all the plus points, and we connect them together with line segments going around the circle, chords around the circle, and we call all the points within the convex set enveloped by this polygon. We call those the plus points. So the hypothesis will call every point that's inside of this set of convex sets or this convex hull, we're going to call those plus points, and all of those that are not in the convex hull, we're going to call those minus points. And so because we set no restriction on how we arrange the points and assign them +1, -1, we have a total of 2 to the n possible dichotomies that we can describe with this hypothesis set, convex sets. And so in this particular case, all possible 2 to the n dichotomies, regardless of how big n is, all possible 2 to the n dichotomies can be output by this particular hypothesis set. And when that happens, you can produce all 2 to the n dichotomies. This has a term, it's called shatter. And so n points can be shattered by the hypothesis set called the convex sets. And if you think about this feature space as a glass pane, and all of the data points are these dots painted on a glass pane, you can think of this hypothesis set, imagine as throwing it down, and it breaks the pane into 2 parts. One part is the convex hull and its interior, convex set, and the other piece is everything else. Well, if you do that, it doesn't matter how big n is. You can always produce all possible ways you can shatter. You can break this into those 2 pieces so that all the positive points, all the ways you can have positive points and negative points, are possible to be labeled by this particular hypothesis set. And so we say that the hypothesis set, called the set of convex sets, it shatters n data points regardless of how big n is. And so this is our growth function for the convex sets. Let's consider this last point. We have our growth functions and the set of positive rays. The growth function in closed form is n plus 1. For the set of positive intervals, you notice it's more complex. The growth function is 1/2 n squared plus 1/2 n plus 1. And then for h being the convex sets, the growth function is that perfect 2 to the n each time. And so we use our growth function as a measure of complexity of the hypothesis set, effectively counting hypotheses in terms of their ability to produce different labelings, to produce dichotomies. And so we use this growth function for hypothesis set H on a data set of size n as a replacement for m. Now, of course, Given our expression for the union bound or Herfting's inequality, if we replace big M with our growth function, M sub h of n, something interesting happens. Well, we said we want Herfting's inequality to be such that the right-hand side, that upper bound on the probability of a bad thing happening, E in diverging from E out, will be small. Well, how do we make this small, this right-hand side? Well, we have this dampening factor, this negative exponential, and we said if we strike the right balance between n and our error tolerance epsilon, we can make it small, but nixing us was this very large M. And so if M is not quite as big as this negative exponential, for example, if M is polynomial, then this negative exponential will decay this polynomial damping factor faster than the polynomial can increase. And so with this, if our growth function is polynomial, then learning is feasible because we will get this right-hand side of the union bound or Herfting's inequality to be small as long as this growth function is polynomial. And so now if we want to prove if learning is feasible, all we have to prove now is that this growth function replacing this complexity measure M, as long as we can prove that it's polynomial, we can prove that learning is feasible. Okay, so we're going to introduce more terminology. If you have a hypothesis set and no data set of size k can be shattered or can have all of its possible dichotomies, 2 to the k dichotomies generated by a hypothesis set, if no data set of size k can be shattered by your hypothesis, then k is considered the breaking point for H. That hypothesis set comes along and can produce all 2 to the n, all 2 to the n, 2 to the n, and all of a sudden the data set size increases to a point where your hypothesis set is no longer descriptive enough to be able to produce all 2 to the n dichotomies. And so we call k then the break point for your hypothesis set H. And so the break point k is that data set size of your in-sample point size, such that the growth function is less than 2 to the k. And so for the 2D perceptron, what did we see? We saw for the 2D perceptron is that when k equals 3, we could generate all 2 to the 8 dichotomies. But once k got to 4, we could only generate 14 of the 16 possible dichotomies. So when we went from a data set size of 3 to 4 for the linear perceptron, the line in the plane, it broke. It was no longer expressive enough to be able to produce all 16 dichotomies. And so for the 2D perceptron, the breakpoint k is equal to 4. A bigger data set, once we reach k equals 4, can no longer be shattered. The perceptron can no longer express all 2 to the k dichotomies. Okay, so let's take a look at the set of positive rays. So for the positive rays, if we have a data set of size 1, well, the number of dichotomies it can produce is 2, right? Because if you have 1 point, it can be red or it can be blue. So if that point is red, the positive ray, if it's red, the positive ray is here. If that point is blue, the positive ray is anchored here. So once we go to a data set of size 2, well, what can we generate? We can generate a dichotomy like this. We can generate a dichotomy like, if we generate a dichotomy like this with a positive ray, yeah, we can do that. We can generate a dichotomy that's completely red. We can generate a dichotomy that is red here, blue here, by anchoring it like that. But we can't do the opposite. We can't have blue followed by red. And so once we reach a data set size k of 2, the positive ray breaks. And so the break point of the positive ray is going to be 2, k equals 2. For the positive interval, let's see. We have a data set of size 1. So if n is 1, that's 1/2 plus 1/2, that's 1, plus 1 is 2. So if we have a data set of size 1, we can make it with a positive interval. We can make it either red or we can make it blue. If we make it blue, we just straddle it between the two anchors for the positive interval. If we make it red, we don't have it straddled, so we can produce that. For k equals 2, well, what can we have? We can have red followed by blue. We can have blue and then red. We can have red, red. We can have blue, blue. And if we want this red, blue, we straddle the one we want to be blue. We can straddle that one to make it blue. We can straddle none of them to make them all red. We can straddle both of them to make them blue. So we can produce all 4 dichotomies when we have a data set of size 2. The positive intervals can produce all 4 dichotomies. But when we go to 3, we cannot produce all 8 dichotomies. And this is an example of dichotomy that the positive interval cannot produce, because how it works is all of those that it straddles are going to be blue. And you can't have red in the middle and straddle to get blue on the left and right-hand side. And so the breakpoint for the set of positive intervals, that hypothesis set, the breakpoint is 3. Because once you go to from a data set of size 2 to a data set of size 3, you can no longer produce all 2 to the 3 or 2 to the k dichotomies. And so it breaks. You can't shatter a data set of size 3. When we look at the convex sets, well, the convex sets, we have all 2 to the n possible arrangements of data points assigned as red and blue labels plus 1, minus 1 labels. And we can therefore, regardless of the size n, we can shatter all data sets of size n because we can produce all 2 to the n many dichotomies. And therefore, the breakpoint k is equal to infinite breakpoint. So that means the set of convex sets, that hypothesis set, is infinitely expressive. And so if we look at the complexity, well, the positive rays is simpler, less expressive. Positive intervals is a little more expressive. And convex sets, it's infinitely expressive. And so we can use this idea of a breakpoint to talk about a notion of the expressiveness and therefore a notion of the counts, the size of each one of these hypothesis sets. And so the primary result says that if there's no breakpoint, the growth function of the hypothesis set is exactly 2 to the n. If there's any breakpoint at all, what it means is that the growth function is polynomial in n. Okay. And so this is our primary result. And as long as we can prove that the breakpoint is polynomial, we can actually show that learning is feasible, because then with the union bound for Hertz inequality, we can show that this thing will decay because that negative decaying exponential will overwhelm that dampening of a polynomial growth function. Okay, so with that, we'll end there. And as usual, please stay healthy, stay safe, and I'll see you all on Tuesday.